Welcome to the class on artificial neural networks. This video gives a short preview of artificial neural networks for action learning. So let us think of a table tennis player who practices a new serve. What he's looking for? He's looking to make a point against his opponent. And these points are rewards. Think of a little boy practicing the piano. He's looking to make a good impression. So these are very vague notions: success, learning from mistakes, looking for rewards. But we believe that this is really the way humans and animals learn. If you train an animal to perform a little trick, well, you will give him a goodie for a good performance. For humans, is the feeling of the success or compliment that serves as a reward. So there are rewards, there are values attached to actions. And in the previous little video on classification learning in neural networks, this notion of value was not really there. There was no notion of reward. Now, reinforcement learning is a subfield of artificial neural networks that studies learning based on reward. And again, you see this connection between biology and real applications. What could these real applications be? A real application of reinforcement learning is an application in games such as chess and Go. And deep reinforcement learning in deep neural networks has given amazing successes. So the best neural networks beat masters in Go, they beat masters in chess, they beat the best traditional programs trained on artificial intelligence principles. And they do this just by training network, the weights in neural networks. So what is such a neural network built of? Well, it's built of neurons. So for example, in chess, you give the input position of the current position as an input to the neural network. And then this information flows across multiple layers, many layers. And in the end, you have different outputs. And these outputs will, for example, for coding certain actions like advance the king. But then we don't have yet this notion of value of an action. So what we do is we have a second output, which is not really an explicit output. It's an implicit output that learns to encode the probability to win given the current input, which means given the current position on the board. And then this information about value or differences of the value in the current position and the next position is used to train a neural network and to plan ahead. As before, learning is based on changes in the connections. And the aim of learning is twofold. It's to predict the value of a position and also to predict the best action, such as an action like advance the king. Advance the king. And what is the best action? Well, it's the action that makes it most likely that you will win. Let's look at this just in a little bit more detail. So we have 64 different little fields where you can place the chess figures, and this gives 64 positions times 6 different types of pieces. There's a king, there's a bishop, there's a knight. You have 2 different8 and then it's not just the current position. In this implementation, they also looked at the last 7 states. So in total, you have 8 different time steps. And so this gives about 10,000 neurons to encode the input position, the current situation, the current state of the network in reinforcement learning language, the state. And this is given as an input. And then the aim is to learn the probability to win and to predict the best actions. And what are these actions? There are about 5,000 actions because you have the king, which can move north and south and east and west, but you have other figures where the movements are slightly more complicated, so it's many options. And training is done by having one instance of this neural network play against another instance of a neural network. And they just play many, many games. They play millions of games. It takes several hours. And each of these neural networks changes the weights so to have a good value, so to predict good positions. And the planning is always just a few moves ahead. You have 1 second before you take the next action. And with this neural network has been able to achieve absolutely top-level performance. And what I like most is that it really discovers textbook strategies, classic openings that you find in textbooks on chess. It beats the best human players. Sometimes it makes variations of these opening strategies, and it also beats the best classic AI algorithms. This was application in games, but there are people at MIT and many, many other places that also think about how to use the same kind of principles to train self-driving cars. What would be values? Well, it's security, of course, maybe also duration of the travel. And inputs would be video images, would be distance sensors, sensor readings, and the outputs is advance, accelerate, turn left, turn right. So there are real applications of these neural networks inside of neural networks trained by values, trained by rewards. So this class has two main parts. There's one part which I would like to call classification by supervised learning, where we'll look at simple perceptron, we will look at deep learning, we look at convolutional networks, all in the context of classification. We do quite a bit of mathematical theory around it. And then there's another part which is about reinforcement learning, about action learning based on rewards. We treat Q-learning, SARSA, policy gradient, deep reinforcement learning. And the way we will proceed is that we start today with simple perceptrons, and then we switch for the next 2 weeks to policy gradient and Q-learning. Then we do a whole set of deep learning approaches, deep learning theory, and finally we go to deep reinforcement learning, which is really the long-term target of this class. That's the end of this little video, and let's have a little quiz. Please pause the video to think about these questions before I lead you through. Okay, so yes, classification aims at predicting the correct category, such as car and dog. Classification is not based on reward, but reinforcement learning is based on reward, and reinforcement learning aims at optimal action choices.